Yes, we are applying the LCO principle to establish various molecular orbitals and their energetics, distribution of electron, and explanation of bond order of the molecule and magnetic property. For that, we should take one example. Let us see the next second example. That's a beryllium diatomic molecule. Whether it exists or not, let us find. Let us understand construction of various molecular orbitals for homonuclear diatomic beryllium molecule B2 molecule. Once we construct the molecular orbitals, we need to distribute total electrons in those molecular orbitals. And distribution of molecular orbitals will help us to find bond order and to describe magnetic property. While establishing molecular orbitals, we will follow LCAO method. What is that LCAO method? It says three essential conditions are there to form molecular orbitals. The first condition, combining atomic orbitals should be of same or similar energy. Second condition, combining atomic orbitals should have same symmetry. And third condition, combining atomic orbitals should undergo appreciable overlap. If I have to talk about beryllium, its electronic configuration, atomic number is 4. So electronic configuration 1s2, 2s2, 2p0. 1s orbital is a inner shell orbital, is an inner orbital. It is in case of each beryllium. So when two beryllium atoms come together, come closer, they do interact, they do overlap. 1s orbital being inside doesn't experience any kind of interaction, any kind of overlap, no additive, no subtractive. So whatever electron density is there in the 1s orbital of each orbital, 1s orbital from each beryllium, it will remain as the same. So overlap integral will be 0. It means the orbital will remain non-bonding. Its energy will be same as the energy of combining atomic orbitals. It is not represented in this MO diagram, but those orbitals are there in the lower energy. After that, the 1s orbital, next energy level is 2s. What is the symmetry of them? They are with sigma symmetry, because whatever the internuclear bonding axis is there, whatever the z axis is there, around which if we rotate that s orbital, then the wave function throughout the rotation will remain same, because s orbital is spherically symmetric. S orbital has no node. It can be with positive wave function either, or it can be with negative wave function. So there is no change in the wave function by rotation. So symmetry is labeled as sigma kind of symmetry. So sigma symmetric 2s orbital and sigma symmetric other 2s orbital, they will interact to produce sigma symmetric bonding orbital and sigma symmetric antibonding orbital. We represent bonding orbital by simply sigma followed by the type of atomic orbital, label of atomic orbital, that's a 2s, means sigma 2s. And we label antibonding orbital by asterisk, sigma asterisk 2s. Bonding orbital, because of the constructive interference, because of the positive overlap integral, decreases in energy. And antibonding orbital, because of destructive interference, because of negative overlap integral, increases in energy. So sigma 2s and sigma star 2s, these are the two molecular orbitals resulted from the combination of two atomic orbitals. Those are 2s orbitals. Let us come to the higher energy level orbitals. In 2p sublevel or 2p subshell, in the 2p subshell, we are finding three orbitals, 2px, 2py and 2pz. This is the case on each beryllium atom. Convention we need to follow. Conventionally, what we consider the internuclear axis, bonding axis is z axis. Reasons are there for that, but at this moment, remember,
bonding axis is our Z axis. So along bond, which orbital from each beryllium will be there? That's a PZ orbital. And perpendicular to the bond direction, px and py orbitals will be aligned. Let us talk about the pz orbital. Pz orbital symmetry. It is along the bond. It is along internuclear axis. Actually, it is along principal axis. If you rotate that pz orbital around that internuclear axis, then one lobe is positive, will remain positive only. Negative lobe will remain to that side only. So there is no change in the wave functions in pz orbital as was happened for the 2s orbital, due to which what will be the symmetry of that pz orbital? Sigma. Yes, as per our first condition, energy should be same or similar. Energy is same here because those pz orbitals are from the same beryllium element. So first condition is fulfilled. Second condition, same symmetry. Yes, both have the sigma symmetry. Third condition, appreciable overlap. Yes, this is outer orbital, so appreciable overlap will be there. So resultant bonding to pz orbital and antibonding to pz orbital with symmetry sigma. How can we represent that? Sigma to pz and sigma star to pz. So see, the lower energy orbital sigma to pz and higher energy sigma star to pz. Here somewhere problematic energy level arrangement you will feel, because sigma to pz is decreasing in energy but not to great extent, and sigma star to pz is increasing energy to great extent. Larger energy gap is there between sigma star to pz and combining atomic orbitals. I described that. Wait, let us think about the combination of 2px orbital from one beryllium and 2px orbital from other beryllium. 2px orbital, how we consider the 2px orbital? One lobe is towards us, other lobe is away from us. One lobe is positive, other lobe is negative. If we rotate that 2px orbital around the internuclear axis, around the Z axis, around the bonding axis, we will find one time after rotation the positive lobe may be away from us, will come towards us, negative lobe which was towards us will go away from us. So there is exchange of the wave function. So it is not symmetric about the bonding axis. It is not symmetric about the Z axis, and not symmetry is represented by term pi. So pi is the symmetry of the 2px orbital. Similarly, pi is the symmetry of the 2py orbital, and the lobes are along the x-axis. So as per the Lcao method, energies are same, symmetry is same, appreciable overlap. So two atomic orbitals will combine to produce two molecular orbitals, one bonding, one antibonding. Bonding molecular orbital we are labeling by pi to px, antibonding orbital we are labeling by pi star to px. The energy with which bonding orbital decreases, that much amount of energy increases there for antibonding orbital. Here in symmetric distribution, symmetric energy level arrangement we are finding. As I discuss the formation of pi to px and pi star to py, similarly the lobes along the y-axis, one upper lobe and lower lobe, one lobe is positive, other lobe is negative. If you rotate that py orbital around the internuclear axis, you will find one time positive lobe will come to negative, negative will come to positive. It means there is no symmetry around internuclear axis. So what is the label? Pi. So that pi orbital, that's a 2py orbital, and other 2py orbital will interact to produce pi bonding orbital pi to py and pi antibonding orbital pi star to py. Here you will find energy of pi to px and energy of pi to py are same. Those are degenerate. Similarly, energy of antibonding, that's a pi star to px and pi star to py, those also are same. Those are degenerate. In this MO diagram, I represented sigma category of interaction by purple color and pi kind of interaction by green color. Now let us understand the energetics or the energy levels of pi to px, pi to py and sigma to pz. Basically, sigma bond we consider as a strong, sigma interaction we consider strong, axial interaction, head-on interaction, head-on head interaction we consider as a strong. So sigma to pz orbital should be of low energy, should be stable compared to the weak pi interacted bonding orbital pi to px and pi to py. It is our usual expectation. But reality is different. Reality is represented there. Reality is sigma to pz is of the higher energy than that of the pi to px and pi to py. The main reason for this you will understand if you go through the video making sense for MO diagram for nitrogen molecule. The answer is shortly I inform here. Their detail I discuss. The interaction between the sigma 2s and sigma 2pz, that's the internal interaction between the molecular orbitals, gives this result. Similarly, there is interaction between the sigma star 2s and sigma star 2pz, internal interaction, due to which there is a considerable increase in the energy of sigma star 2pz and there is a increase in the energy of sigma 2pz, causing decrease in the stability. Causing sigma 2pz orbital is of higher energy than that of the pi 2px and pi 2py orbital. So go through the video, concept will be clear. Otherwise, time being, remember such kind of diagrams are there for low atomic number diatomic molecules or the where energy gap between the 2s and 2p is less. If the 2s and 2p gap would have been more, no, then as per our expectation, the MO diagram will be there. Yes, time will come. At that time, we'll have the discussion on that. So what is the energetics? So what is the energetics now? What is the energy level? Lowest energy, non-bonding orbitals. So we represent as a KK. Next, sigma 2s. Next, sigma star 2s. Next, pi 2px is equal to pi 2py. Same energy. Then sigma 2pz. Then pi star 2px is equal to pi star 2py. And last, highest energy level orbital is sigma star 2pz. If I have to distribute electrons, how many electrons are there in total? 4 electrons from each beryllium. So 8 electrons are there. How can I distribute those 8 electrons? 2 electrons in K shell, means 1s orbital of 1. 2 electrons in other K shell, so 1s orbital of other. So KK, how many electrons are there? 4 electrons, which are not represented here, but those are there in the molecular orbitals. Those are non-bonding molecular orbitals. That is a part of molecule. Afterwards, energy level is sigma 2s. How many electrons it can accommodate? 2 electrons. So total now 6 electrons are completed, 4 in the inner orbitals and now 2 in the sigma 2s. Now left 2 electrons. Those 2 electrons will go in the higher energy level orbital. That's the sigma star 2s. Now what is the use of this electronic distribution? We can find out bond order and can describe the magnetic property. What is a bond order for this beryllium molecule? What is the formula for bond order? Number of electrons in bonding orbital minus number of electrons in antibonding orbital divided by 2. So pair of electron in bonding will help us to establish one bond and pair of electron in antibonding will oppose to form one bond. It's the meaning of this formula. Let us calculate number of electrons in bonding orbital. There are only 2 electrons in the sigma 2s, that's the bonding orbital, and 2 electrons are there in antibonding orbital. So 2 minus 2 divided by 2. What is the answer? 0. So in B2 molecule, there is a no bond. It means diatomic beryllium molecule does not exist. It is the answer by molecular orbital theory, which is a reality. Actually, if it not existing, then there's a no question of magnetism. Let us see how can we represent the electronic distribution. Yes, this is a way by which we can represent the electronic distribution. Beryllium 2, so B2 represented. 3 horizontal lines means equivalence it is representing. And in special bracket, the all orbitals are represented. By green blue color, I represent the non-bonding orbital. By white color, I represented the electrons in bonding orbital. By yellow color, I represent the electrons in anti-bonding orbital. So KK, the first shells, 4 electrons are there because in each K, 2 electrons can be accommodated. Then sigma 2s orbital, 2 electrons. Sigma star 2s, 2 electrons. Pi to px orbital, no electron, but has same energy to that of the to py orbital, pi to py orbital. So I represented is equal to sign there. Pi to py, 0 electrons. Then I represent comma, means energy gap is there. Next higher energy level orbital. That's a sigma to pz, 0 electrons. Afterwards, next higher energy orbital. Actually, it's a set of orbitals. Pi star to px and pi star to py. Both are degenerate. Both have the same energy. How many electrons are there in pi star to px? 0. And how many on pi star to py? 0. And highest energy orbital sigma star to pz, 0 electrons. So this is a way of electronic representation. Now it is for diatomic beryllium molecule.
As a homework, one simple question. Does B2 molecule exist? Yes or no? That you have to answer in the comment box. I am waiting for your answers.
Like a bird.